Good morning, students. Today I am going to present third chapter or third module, which I call the boundary layer theory and its application. This is the first lecture in this context, and this lecture will be focused on the introduction to the boundary layers. So the objective for today's class is I would like to explain what is the boundary layer and introducing the boundary layer on a flat plate. So I will start this lecture by showing you a video clip of a very old.
If fluids did not.
So this part of the video shows a cylinder with a rigid flat plate attached to it and a uniform stream of fluid which is coming over there. So let's begin.
Have viscosity. When a real fluid, water, flows around the same shape, the flow is quite different. Boundary layers, thin layers of fluid in which viscosity affects the flow dynamics, are formed along the surfaces of the object. The behavior of these boundary layers under the influence of pressure gradients can, in some cases, drastically alter the flow.
Now, if you see this video, this part of the video, you see at the first start of the video, which I have shown, it was the potential flow solution shown in the video. Then there was a steady flow of water which is coming under the solid surface, and it shows that the viscosity affects the flow. Okay. Now, what I wanted to show you is, if you concentrate on the cylinder surface, circular cylinder surface, there you see a very thin band of fluid in which there is a lot of activity. Um, so that is the whole point. So that band of activity is the region near the surface where the viscosity dominates the fluid flow. So that is what I wanted to show it that in this part of the video. Now I will again change the video. Now, right now, if you see the clip at this position, there is a airfoil, and in the airfoil there is no separation right now, or any. All the streamlines are parallel to each other, nearly parallel to each other. So that means there is a very this is the potential flow solution. Now, if you change the angle of attack of the attack, now then you will see more activity.
Because the Reynolds number is large, influences of viscosity are confined to a narrow region.
Now, since again if you see here, which is so if the Reynolds number is very large, as the video clip says, the influence of vorticity or viscosity, sorry, not the vorticity, but viscosity is confined to a very narrow region, and this region right now is you are not able to see. Okay, but now we will see some
close to the surface of the wing. The primary effect of viscosity is simply to create a drag force on the wing through the integrated effect of surface shear stress. As the angle of attack is increased, viscous effects become more pronounced. Pressure gradients imposed on the boundary layers become more severe, and separation occurs on the upper surface. Now the airfoil is stalled. A region of recirculating flow is formed over the upper surface of the wing. In order to understand how viscous forces can influence the entire flow field, we shall look at what causes boundary layers, how they grow, how they respond to pressure gradients, and the difference in behavior of laminar and turbulent layers. Before attempting to understand the boundary layer flow over this object, we shall look at the flow of a viscous fluid along the flat plate alone. These streamlines of water flowing in a channel are made visible with hydrogen bubbles generated by electrolysis. The flow is uniform and laminar. The fact that the timelines, the vertical patches of bubbles, remain perpendicular to the streamlines shows that the unobstructed flow is free of vorticity. Here is the flow over a plate. The flow is two-dimensional and laminar. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present.
Now, if you look at this, I have paused the video. If you look at this, the plate, before the plate, the flow is basically all uniform. Now that means that there is no effect of viscosity on the upstream side of the plate. But if you will see that very near to this, very near to the plate, there is a thin, very thin region of flow where there is the streamlines are different from the uniform streamlines. So there is a very thin region of activity of the flow. The pic near this, the attached pic shows is a part of this video. It shows that now there is the plate and the very thin region which we have zoomed onto that, and this zoomed region shows the activity of the viscosity. Now this thin region is basically the boundary layer. So it is very so if I go to the next slide, it shows 4 examples of flow. So one is this same cylinder on which you have seen the flows, and one is the flat plate. The other is the curved curved beams or the streamlines of an airfoil over an airfoil, and the other is internal flow in a pipe. In all these flows, there will be always a boundary layer associated with that when the flow of the fluid is viscous. Now, if you see on the flat plate, the streamlines are still uniform or straight. The streamlines are straight, but there is I have the yellow line which shows the edge of the plate, where the edge of the flow over the flat plate. Now, the perpendicular to this direction, there is an activity, or there is a change in flow, change in the velocity. Similarly, at all stations along the x direction, there is always a boundary layer which is formed. Now, if I see if I see this in 2 dimensions of a flow over a airfoil, well, you see that the blue light shows the edge where the action of viscosity takes place. And in all these flows, if the separation is not there, then you will find the uniform the velocity profile to be like this. If I go to an internal flow over a flat in a pipe, the viscosity boundary layer starts to grow from the edge of the boundary layer. So there are 3 regions in this one, which is one region is very near to the upper surface, upper plate, and the other viscous dominated region is very near to the lower plate. Now these 2 boundary layers starts to grow, and the place where there is no boundary layer, no viscosity, is called the core of the surface, core of the pipe, and there the inviscid flow will be there. Now, if you see that this inviscid flow region becomes thinner and thinner, and the viscous dominated region grows, and the point at which this these two viscous boundary layers meet, after that, all the flow, all the pipe, whole of the pipe is basically a viscous dominated pipe, the viscosity dominated pipe. So after this point, the flow is basically a fully viscous flow or fully developed flow. This length by which we uh, this is called the entrance length, and normally this is a function of the Reynolds number. So it is normally like 100 times of diameter. So you can see, you can visualize that if it is 100 times of diameter, that means diameter of the pipe. That means how long the pipe you need to actually perform an experiment on in the viscous region of the flow. Now, what is the effect of this boundary layer? These boundary layer basically, as the video shows, and that this viscosity basically influences the shear stress on the surface, and this shear stress or the skin friction integrates or in turn causes the drag force, a force on the body. Now, for an engineer, this drag force is an important concept. Now, the contribution of Ludwig Prandtl, who basically gave the boundary layer theory, which we will discuss in this chapter, was that he was the first person to give a accurate, to a not very accurate, but a nearly accurate prediction of the drag force on a flat plate or on a airfoil, and which helped basically in developing better or the new age fighter planes um, before the World War. So that was the contribution of this theory towards the fluid mechanics or the general concept. Now, it this type of boundary layer is always formed on every surface, provided that the Reynolds number is sufficiently high. Now, I will now discuss boundary layer on a flat plate slightly in more detail. Now, if you will see that there is a flow which is coming from the x direction, and my perpendicular direction is the y. Okay. Now, if I see that, now this is the growth of the boundary layer edge which I am trying to talk about. Now, this line, this light blue line, basically separates the no viscosity region and the viscous dominant region. Now, what we call the no viscosity region behaves as a potential flow region, and the viscous region behaves as viscosity dominated region as the viscous region. Now, if I take two stations, x1 and x2, and draw the velocity profile or held a probe along the y direction, perpendicular y direction, I will, what do I expect? Now, I know that for sure that at the surface, because of the no slip boundary condition, the viscosity is zero. Sorry, the because of the no slip boundary condition, the velocity at the surface of the flat plate is zero. Now, I also know that at the in the region where there is no uh, there is no no viscosity is present, that is, it behaves as the potential flow region, the the velocity u infinity will always be will not be changed. So that means if I draw a better profile like a station 2, which explains much more detail, the velocity at the after the edge of the boundary layer is basically more than u infinity, or is nearly equal to u infinity. That means the free stream velocity, which is at the inlet of the flat plate. Now I have tried to plot the velocity profile at at uh, at different heights, vertical direction height h. So at very far away from this is the edge of the edge is this where where u becomes directly equal to u infinity, and and y is equal to a certain small segment of this is the part where the u becomes nearly equal to u infinity. Now at the edge of the boundary layer, okay, um, u becomes equal to the nearly equal to the u infinity. Now in this part, we do not know. Basically, we do not know what type of actions are there. So we set a velocity probe, a probe to measure the velocity at different sections of in the wall normal direction. That is the stream, and that is the y direction here. The whole direction, y direction at different points in the y, like 0.1 times of h, 0.2 times of h. Then you will find at different values of 10%, 30% of the u infinity, 40%. But the point, but, but the point at which it reaches 99% of u infinity, we call that point to be the that length to be the surface of the that length to be the that distance to be the boundary layer thickness. Now, if you measure this at other sections, you will find that this boundary layer thickness is a function of the x direction, that is the streamwise direction. Now, let me formally write what is the boundary layer. When a fluid flow takes place over at a sufficient high velocity, that is higher Reynolds number, it is observed that the viscous effect or the transfer of momentum takes place in a very thin region or region close to the solid surface. The thin region is referred as the boundary layer. Now, why this whole concept of defining the boundary layer is that we want to see that what type of equations or what type of can we solve the boundary layer, because we know the solution of how to obtain the solution in the potential flow region. That means outside the boundary layer, we know how to solve, but inside the boundary layer, the whole Navier-Stokes equation is valid. Now, Navier-Stokes equation is two or three dimension partial differential equation with a high degree of nonlinearity present in that, which is difficult to solve. To so uh, so to simplify that, the Prandtl gave this idea of develop this boundary layer equations, which basically says that we take the Navier-Stokes equation, full Navier-Stokes equation, apply appropriate scaling and non-dimensionalization, do order of magnitude analysis, and then use the reduced and see that which terms are bigger and which terms are smaller, and we get the boundary equation. Now, to define more the boundary layer structure, I will use the same slide. So you can see that the edge of the viscous boundary layer is not a sharply defined entity. So that means there must be a certain way to quantify it. So this in the boundary layer flow, the velocity, all the actions or the variation of velocity, nearly all the variation in velocity is basically in this delta x. So the boundary layer region is between 0, starts from the 0 in y direction to less than delta x in the x direction. Now, for quantitative thickness thinking, this delta x can be taken as 0.99 or 99% of u infinity. Now, how am I going to what is the relationship between delta x and Reynolds number? That is the next important question. Now, to do this, uh, uh, we will. I have two arguments which have been put forward. One is from the your one is by using the second year fluid mechanics course which you have studied, the Reynolds transport equation. So if you remember that Reynolds transport equation, we apply this Reynolds transport equation of momentum and mass conservation on the control volume shown. So the green line, ABCD, is the control volume on which we are going to apply A, AD, AD and BC are both streamlines. That means there is no vertical transport of mo momentum or mass across the streamline. So, and because BC is nearly the edge of the boundary layer thickness, is the boundary layer thickness. We have assumed it to be right now. If you have a small area, then you can see that it is basically a straight line. Uh, there is no mass flow or momentum transfer across the string line, and the stress above that, shear stress above that is zero, but shear stress inside the ABCD control volume is not zero, or neither at the surface AD is zero. CD is basically the boundary layer thickness. The length CD is the boundary layer thickness, and AB is certain H, just to define that. And this is perpendicular in the B direction, in the direction of the paper or the screen right now, that is Z direction. This is has a thickness B. Okay, the momentum equation, which is shown over there. You can see this maths which I have done. You can see from here that the drag force is the only force in the x direction which has to apply, because shear stress is not zero at the surface AD. And from there you can see that the drag is equal to rho u infinity square b into h minus rho b into the integral from 0 to delta u square dy. Now, which by applying the conservation of mass can be reduced to equation number 3. Now, this procedure was given by von Karman in 1931. He was one of the students of Prandtl. Now, if I assume a velocity profile at the exit CD, now if I assume a velocity profile which follows the any which can be any shape, but here I have used a certain velocity profile which is very much prevalent. If you assume a different velocity profile, the constants 5.5 may differ, but the relationship will always come out to be the similar. So if I assume that and do the maths, okay, which has been explained, I get the expression that delta by x is basically 5.5 times of re x raised to the power of minus r. Now there is another argument which I can follow, is by using the dimensional analysis. Sorry, from the help of the Stokes first problem, which was solved in your exact solutions or the last chapter. What we learned from that was so the firstly which what we want to do is that the boundary layer thickness, how it is related, what is the function by which it is related to x us. Us is the scaling velocity, or u infinity in this case, and I am going to use this the expression or the data from the last exact solution, the Stokes first problem, was that the delta x and the viscous penetration length was proportional to the viscosity as well as the time scale involved in the flow. Now, time scale, which is spent by the fluid in the neighborhood of the surface, is basically the now you can assume, now you can visualize that if a particle or the fluid particle is traveling on a flat plate, the length that is in the wall streamwise direction is the x, upon x is the length in that direction. So that means, and the velocity by which it is traveling is u infinity. Okay. Now, if it is the order of time, so that means that the maximum amount of time which it will take, or the recognizable unit of time, will be the velocity by which this particle crosses the crosses the plate. Now, if the plate length is L and velocity u, then it will try it will the it will be L by u infinity or u scaling or u infinity. Now, if I am at a particular station x, then this length will be x divided by the scaling velocity us. Now, if I substitute this into this the delta x is equal to is proportional to nu times of ts, I get that this expression, and finally I get delta x by x is k times of rex raised to the power of minus half. Now, what do I get it from here? Is this, which are the more important concept, is that if the Reynolds number, the local Reynolds number, x, since Rex I am talking about, so x is the point at which the Reynolds number is calculated in the streamwise direction. If the Reynolds number x is much greater than 1, that means the velocity is sufficiently high, which if you go across to my first, where I discussed in words the boundary layer theory, boundary layer, the sufficiently high, you can see that from here, sufficiently high velocity or high Reynolds number was the sufficient condition for this, or necessary condition for this. So if it is like this, then if the Reynolds number is sufficiently high, then delta x by x is much less than 1. So that means delta x is much smaller to x. That means, as if you will remember at the start of the presentation, I showed the picture here. Since so x will be the direction of the plate, of the length of the plate, the delta, the boundary layer thickness, is a very small region. So this um, this last part of this mathematical analysis gives us the same words, same thing back. So in other words, the viscous layer or the viscous boundary layer is very thin in comparison to the streamwise distance from the leading edge. Now the second thing, which is important thing, which is gives is the boundary layer grows along the streamwise direction as delta x is proportional to x raised to the power half. So these two things, that means as you go downstream of a plate, downstream of any surface, whether it is a plate, airfoil, cylinder, or anything, boundary layer will always grow. That is the important thing. So that is these two are the takeaways from the initial introduction of the boundary layer theory. Remember that. Remember this relationship. Delta x by x is proportional to re raised to the power x minus half delta x by x. This is one important relationship which gives you both this argument that delta is much smaller to the x is smaller to x, and delta x is proportional to x raised to the power half. Therefore, you can see that from our graphs of the boundary layer. You can see the boundary layer thickness which I have drawn. This is always growing. As you go in the x direction, the boundary layer thickness is always growing. So this is the important. These are the two important thickness. Thank you very much. And this is the last thing. In the next class, I will show you how to use the scaling argument which I have, scales which have been introduced by this in this part of the work, in this part of the class, and develop the equations from here. Thank you.